Okay, so now let's start from the beginning how we can do the functional data analysis. So as we just mentioned that for the functional data, generally we are working on to analyze the curves, right? But in the reality, when we have this, in practice, we can only have some discrete measurements on these curves, right? So here we have, this is one example of the temperature. Actually, this is, I believe, the average temperature in Vancouver over 1 year. So we have the daily average temperature in Vancouver. So we have these discrete measurements of the temperature. Is a pretty frequent measurement. So the first step we want to do when we do the functional data analysis is to how to convert the discrete measurement on the functional data to a continuous function like the right panel. Okay. So when we learn the multiple linear regressions, basically we will write the response y as a linear function of the covariates x1, x2, right? And so when we have this impression, we basically assume the y is linearly increasing with these covariates x1 to x2, right? And in some sometimes we will try some like a nonlinear trend. We will using the quadratic or cubic term of this covariate function. More generally, when we want to capture more complex trend, we can write down this function as a linear combination of some basic functions. So here, we will write the f of t as a linear function of this basic function. So here, phi j of t is some basic functions, and cj is the coefficient to these basic functions. So then we can choose some powerful basic functions, phi j here, and then we are able to capture any nonlinear trend f of t here. So from now on, we will first introduce some commonly used basic functions like phi j of t, and then we will, after we know how to choose the basic functions, we will learn how to estimate the coefficient to these basic functions. Any questions? Okay, so the most simple basic functions is the monomial basic functions. So here, the first monomial basic functions is phi t equal to 1, basically the constant. Okay, so if we just using these constant basic functions to estimate these temperature curves, we will basically just get a constant here, right? Constant curve here. Basically, it's the average temperature over the whole year. Okay, and then we can add the second monomial basic function. So the second monomial basic function is phi t equal to t. Okay, so it's a linear function. So then we can have this linear combination of these two basic functions to approximate these temperature curves, and you can, surprisingly, we will have a linear trend, right? Okay, so basically you will fit a linear regression function regression to this temperature curve. You can see the fit is not satisfactory for sure. And then we can add the third monomial basic functions, which is phi t equal to t squared, right? So when we add the second, the quadratic term t squared, you can see now these three basic functions are able to capture the temperature curves much better, right? But still not satisfactory, because if you look at this part, it didn't capture this peak here, right? And also didn't capture this left tail boundary part well enough. Okay, so we can try adding the fourth monomial basic function, which is a cubic function of t, so phi t equal to t2 cubic. And so after add this, and you can see with these four basic functions, it is able to capture the boundary part reasonably well, but it didn't still cannot capture the peak part, and this the middle part actually not is consistently lower than the estimated function, right? So so we can add the fifth monomial basic functions, and now it seems better, right? But still, didn't capture the peak here, and also the left boundaries. It has this weird kind of small tails going up, right? So this is definitely not the trend of this temperature curve. So we can add more, and eventually, when you add a lot of these monomial basic functions, eventually it will capture these temperature curves reasonably well enough, right? But you can see actually on the right boundaries here, this has small tails going up, right? Yes. Monomial, basically here, we try to capture the temperature curve as using a polynomial function of t, right? Yes. And so this is a monomial basic functions. So there's some problem with these monomial basic functions. Basically, you can see here this panel is to try to plot. I think is the 6 basic functions for the monomial basic functions, and you can see here when we include the t to 5th power 5 as basic functions, it suddenly dominate all the other basic functions, right? Because if you think about here, our t is going from 0 to 365. So 365 to 5 is a huge number, right? So therefore, the large terms often dominate the small terms, okay? So which make the computation much more unstable. In other words, a small change on the coefficient to the large terms, it has a dramatic change on the fitted functions. Okay, so therefore, in reality, we never using monomial basic functions to approximate a function curve or curve. Another drawback for using monomial basic function is that when we estimate these functions in functional data, another important job in functional data is try to capture the derivative or the rate of change of these functions. So here, I'm going to show you this is kind of what this is the temperature function, and this is the derivative of the temperature function. Suppose this is the true derivative of the temperature function, and so you can see here for these derivatives, actually it has so for the original temperature curve, it has a pretty simple trend, right? Basically, it's just going up, and so like higher temperature in the summer and lower temperature in the winter, and gradually going up from the winter to the summer and then going down to the winter again, right? So this is a pretty simple trend. But if you look at the derivative, you can see the derivative actually has some local boundaries, peaks in these derivatives. So the trend looks more complicated than the function itself, right? Actually, this is true for most functions in reality. So if you think about when we drive the car, right? So the speed, so basically the acceleration is the derivative of the speed function, right? So if we drive the car, and so maybe you can maintain the speed relatively around 50 kilometers per hour. But actually, when you drive the car, actually the acceleration actually changes a lot, right? When you're going up a hill or you want to turns, actually you have a lot of change in terms of the change of the speed, right? But the speed curve always will be around 50. So in other words, the derivative or the acceleration trend will be much more complicated than the speed itself, right? So that's kind of a commonly feature we found in practice. So therefore, generally we believe the derivative of the function will be more complicated than the function. So when we use a monomial-based function to estimate, to approximate a function f of t, and when we take the derivative, actually the derivative will be, if we use them up to a degree k polynomial based to approximate f of t, the derivative will become degree k minus 1 polynomial function, right? In other words, when we use monomial-based functions, we basically assume the derivative is simpler than the function itself, right? Because it's using lower order of polynomial functions to approximate this derivative. Therefore, one common problem to using monomial-based function is that the derivative tend to be much simpler than the true derivative it should be. Okay. So this is a kind of another drawback for monomial-based functions. If you look at the second derivative, so you can see the second derivative of the temperature is more complicated than the first derivative, right? Which is makes sense intuitively. But if you look at the monomial-based functions, actually the estimated second derivative is even more smoother, because when we use the estimated second derivatives, the degree will become capital K minus 2, right? So it becomes simpler. Therefore, in reality, we will never recommend the monomial-based functions. Okay, we never use polynomial functions to approximate the curves. So actually, in mathematics, there's a big research area called approximation functions. So they have developed studied all different kind of basic functions to approximate the functions accurately. One popular basic function they use is the Fourier-based functions. Okay, so here this is actually Fourier-based function is a very popular basic function used when we do the functional data. So here are the form of the Fourier-based functions. So basically, they are sine and cosine functions of increasing frequency. So basically, we have the first Fourier-based function is a constant, phi t equal to 1. The second basic function will be sine omega t. The third one will be cosine omega t. So this you can see here. This sine cosine function will appear at the pair. So we always will have a sine omega t, cosine omega t, and then we will have a sine 2 omega t and cosine 2 omega t. So here omega is defined by the period of this oscillation process. basically you can calculate that omega is equal to 2 pi over p. So p is the period of this oscillation behavior. For example, for the temperature, if we believe the temperature has this annual oscillation, so the p here will be 365, right? So therefore, when we approximate the temperature curve, we will using omega equal to 2 pi over 365. And so because in the Fourier basis functions, we always will using these pairs of sin cosine function. Therefore, the number of Fourier basis functions will always be an odd number, right? Because will be always of these pairs plus these constant basis functions. Okay. So this is the Fourier basis functions. So now let me show you how this Fourier basis function working when we approximate the same temperature curves. So this is using the first basis functions, phi t equal to 1, the constant basis functions. Again, this is the same, just the constant functions. And then we add the pairs sin omega t, cosine omega t, and we set omega equal to 2 pi over 355. And you can see here, just using adding these two pairs of sin cosine functions, and you can see the approximation actually is pretty good already, right? Yes. And then we can add another pairs, sin 2 omega t and cosine omega t, and you can see actually the fit is pretty good now, right? Yes. And we can add another pairs, sin 3 omega t and cosine 3 omega t, and so the fit is still improving, and we can try another pairs, sin 4 omega t and cosine 4 omega t, and you can see the fit is pretty good. And also you can see here, not only you can capture the peak of this temperature curve, it also don't have the weird increasing shape as the when using the polynomial function in the boundary, right? The reason is because when we're using the sin cosine functions, we actually assume that this function is a periodic function. Therefore, when we fit this temperature curve, it assumed like this part is connected with the right end is connected with the left end, right? So therefore, it becomes more stable in the boundary. Okay, so that's another benefit when we're using the Fourier basis functions. So we can add in more. So you can see the Fourier basis function actually are able, if we using a limited number of Fourier basis functions, we are able to capture this temperature curve very well. Okay, and so the Fourier basis functions actually has a long history. They are the only alternative to monomial basis functions until the middle of the 20th centuries. They have very nice computational properties, especially when the observation is equally spaced. Maybe you have heard about fast Fourier transformations in mathematics, and it's also very natural for describe the periodic data because these basic functions have the periodic behavior already, right? Okay, so this is the advantage for the Fourier basis function. Therefore, when we approximate the functional data, if the functional data is periodic, we will always using Fourier basis functions to approximate the functional data. Okay, so this is, but in reality, there's often many functions that are not periodic, right? So then, if we're using Fourier functions, there will be a problem, right? So therefore, we are going to learn another powerful basic functions to represent the functions when they are not periodic. Another advantage for the Fourier basic function is that if you look at the derivative of the Fourier basic functions, so here capital D represents the first derivative, okay, with back to t. So you can see that when we take the derivative of the basic function with back to t, so the derivative of sin omega t will be minus omega cosine omega t. I think there's no minus, right? So derivative of sin omega t will be omega cosine omega t. And the derivative of cosine omega t will be minus omega sin omega t. And so in other words, when we take the derivative of the basic functions, unlike the monomial basic function, the complexity of the basic function doesn't decrease, right? You still will using the cosine omega t and sin omega t to approximate the function itself. Therefore, if we use the Fourier basic functions, we are not only able to capture the temperature curve very well, we are also able to estimate the derivative and the second derivative reasonably well. Okay, so this is another benefit when we're using the Fourier basic functions. So here, the two panels here is to show you the estimation for the Vancouver temperature curve. So I believe the blue one is the true derivative of temperature. This is doing the simulation study. So the true one, the blue one, is the true first derivative and second derivative. And then we generated the data, and then we estimated the first derivative and the second derivative. And the red one is estimated the first derivative and second derivative. And you can see that the estimated derivative and the estimated second derivative are both very close to the true derivatives. So this is another benefit when we're using the Fourier basic functions. Okay, so any questions for the Fourier basic functions? Is this clear? Okay. Who have using basic functions in their computing? Can raise your hand? Okay. No? Okay. Okay. So this is the Fourier basic functions. Okay, so maybe we can have a 10 minutes break, and after that we will continue to introduce another basic functions. Okay.